A mysterious celestial body is currently traversing our solar system, leaving astronomers with more questions than answers. We are unable to determine its precise nature or purpose, and it has already moved beyond our direct line of sight. For months, however, this object was under intense scrutiny. It has been designated 3I divided by Atlas and classified as an interstellar comet. A significant body of knowledge has been amassed about this visitor from beyond our solar system. In a mere 4 months, close to 100 scholarly articles have been published on 3I divided by Atlas, supplementing a wealth of other information circulating outside of official channels. Some of these accounts may seem incredible, so our goal today is to sift through the speculation and present the essential facts you need to know about 3I divided by Atlas. Let's trace the path of this interstellar traveler. At present, 3I divided by Atlas is at its closest point to the Sun, a phase known as perihelion. This peak proximity occurs on October 29th, when the object will be approximately 210 million kilometers from our star. To better comprehend this immense distance, astronomers often use the astronomical unit, AU, which represents the average distance between the Earth and the Sunday. The perihelion of 3I divided by Atlas is at 1.4 AU from the Sun, placing it just inside the orbit of Mars. This period of maximum solar exposure is when 3I divided by Atlas will be at its most active. The intense heat will cause a significant amount of material to be ejected from its surface into space. This process, known as sublimation, is characteristic of comets. It's the direct transition of a solid to a gas, as a liquid state is impossible in the vacuum of space. Sublimation is what gives a comet its distinctive appearance, with a hazy aura and a long tail. The aura, technically called the coma, is composed of gas and dust released from the object's solid core. The tail is formed by the solar wind, a continuous stream of radiation emanating from the Sunday. This celestial breeze pushes the lightest particles of gas and dust from the coma, creating a spectacular cosmic display. Regrettably, we are positioned on the wrong side of the Sun to witness this event as 3I divided by Atlas reaches its peak activity. Our view of the perihelion is completely obstructed by the Sun's glare. While we await its reemergence, let's delve into the fascinating story of its arrival. Our tracking of 3I divided by Atlas began in July 2025. It was officially identified by the Asteroid Terrestrial Impact Last Alert System, ATLAS, a global network of telescopes in locations such as Hawaii, Chile, and South Africa. Their mission is to scan the night sky for moving objects. On the night of July 1st, they detected just that, another moving object. It was initially classified as a new asteroid, but then a peculiar detail emerged: its incredible speed. Everything in space is in perpetual motion, and every object in our solar system orbits the Sun, bound by its gravitational pull. Our orbital velocity is what prevents us from succumbing to this gravitational force. The closer an object is to the Sun, the faster it must travel to maintain its orbit. However, if an object moves fast enough, it can begin to escape the Sun's gravity. At a certain velocity, it can break free entirely and venture into interstellar space, the vast emptiness between stars. When astronomers calculated the velocity of this newly discovered object, they were astounded. It was the fastest moving object ever detected in our solar system. To put this into perspective, the Earth orbits the Sun at a speed of 30 kilometers per second. Mercury, which is much closer to the Sun at 4 AU, must travel at approximately 48 kilometers per second to maintain its orbit. The object discovered by Atlas was moving at 58 kilometers per second, and at the time it was still far out, just inside Jupiter's orbit. about 4.5 AU from the Sunday, it was clear that at this velocity, the object was on a hyperbolic trajectory, meaning it would not be captured by the sun's gravity, but would instead pass by and continue its journey back into interstellar space. This confirmed that it had come from the void and would return to it after a brief tour of our solar system. This is when it was named 3, I divided by Atlas, signifying that it was the third interstellar object to be identified. You might be familiar with the first Oumuamua, which was also quite enigmatic, though in a different way than Atlas. The second 2, I divided by Borisov, was less remarkable, behaving much like a typical comet, aside from its interstellar origin. There are 3 key distinctions between 3I divided by Atlas and its predecessors. First is its size. It is considerably larger. Oumuamua was up to 400 meters across, and Borisov was as wide as 1 kilometer, but 3I divided by Atlas could be up to 5.6 kilometers in width. Second is its velocity. Atlas travels at roughly double the speed of Oumuamua and Borisov. The third, and perhaps most perplexing, is its trajectory. Oumuamua and Borisov approached from the northern sky, which is the general direction in which our solar system is moving as it orbits the center of the Milky Way galaxy. So, in a sense, we collided with them. 3I divided by Atlas, however, is not a head-on encounter. It is approaching from the side, almost perfectly aligned with the plane of the planets. Our solar system is a relatively flat disk of matter that formed around the Sunday. Over eons, this material coalesced into planets, moons, and asteroids. But it all remained within this flat plane, known as the plane of the ecliptic. There are a few exceptions, the most notable being Pluto, whose orbit is tilted at a 17-degree angle. This context highlights the remarkable alignment of 3I divided by Atlas, which is only 3 degrees off the ecliptic plane. The probability of such a side-on approach from any random direction in 3-dimensional space is incredibly low, making it a significant coincidence. This leads to an even more profound question. Where did 3I divided by Atlas originate? We know it came from the direction of the galactic core. If we visualize the Milky Way from a top-down perspective, our solar system is located in an outer spiral arm. The bright core in the center is densely packed with stars. To truly understand the origin of 3I divided by Atlas, we need to view the galaxy from the side. Like our solar system, most of the matter in the Milky Way is concentrated in a thin disk. However, there is also a thick disk above and below this plane, a less crowded region where celestial objects can remain undisturbed for extended periods. It is from this ancient region of space that astronomers believe 3I divided by Atlas hails, which could make it as old as 7. 6 billion years, nearly twice the age of our own planet. While we may never be able to trace its journey back to its exact point of origin, astronomers have recently backtracked its path over 10 million years, identifying 93 stars it would have encountered. What is truly fascinating is that over this vast expanse of time, the closest it came to any of these other stars was a distance of 0.3 light years, which is 63,000 astronomical units. In stark contrast, it is currently just 4 AU away from our Sunday. Now, let's explore the approach of 3I divided by Atlas and what we have learned about it. Although officially discovered on July 1st, it was first spotted on May 7th, 2025, in images captured by the Transiting Exoplanet Survey satellite, TESS. TESS, an observatory orbiting Earth, happened to be looking in the direction of 3I divided by Atlas for about a month, providing us with an opportunity to track it as it moved through Jupiter's orbit. The first thing astronomers measured was the object's brightness and its changes over time, which can reveal information about its composition. In the month that TESS observed 3, I divided by Atlas, it traveled about 1 AU closer to the Sunday. Therefore, it was expected to get brighter. Astronomers use the term flux to describe the perceived brightness of a celestial object. The flux of 3, I divided by Atlas, was expected to increase by a factor of 1, 5, between May and June. But the data from TESS showed that it actually increased by a factor of 5. This massive increase in reflected light indicated that it was not an asteroid, but a comet beginning to form its coma of gas and dust. However, two aspects of this observation were unusual. The first relates to the polarization of light. In simple terms, when sunlight hits the cloud of gas and dust around 3, I divided by Atlas, it scatters in different directions. The direction of the scattering can tell us about the material it is hitting. Most objects in space, including the interstellar object 2I divided by Borisov, exhibit mostly positive polarization. 3, I divided by Atlas, however, has a negative polarization, and it is the most extreme negative polarization ever discovered. This suggests that not all solar systems are the same. What is considered normal here may be unusual elsewhere, and vice versa. The second surprising thing about the coma of 3, I divided by Atlas, was that it formed so early, while the object was still beyond Jupiter's orbit, over 5 AU from the Sunday. At this distance, it is extremely cold, and comets from our solar system are typically still frozen solid. The sublimation process that forms a coma usually begins between 3 and 4 AU. This is because comets in our solar system are primarily composed of water ice, which requires a significant amount of energy to melt. As our most powerful telescopes were pointed at 3, I divided by Atlas, we learned that its coma was dominated by carbon dioxide gas. While it did contain some water vapor, the ratio of CO2 was much higher at about 8:1. This is the inverse of what we typically find in comets. Frozen CO2, or dry ice, sublimates at a much lower temperature than water ice, which explains why the coma of 3I divided by Atlas formed so early. As 3I divided by Atlas continued its approach to the Sun, we observed the ratio of CO2 and water begin to shift. By late September, as it passed through the orbit of Mars at just over 1.5 AU, the object began to release a massive amount of water vapor equivalent to a fire hose at full blast. This was more water than would be expected, even from a typical comet at this distance. We had never witnessed such a sudden and abundant release of water vapor. The same can be said for the presence of metals in the coma. During the summer, astronomers detected a small amount of nickel in the surrounding cloud, but no iron. Nickel and iron are commonly found together in celestial objects because they are formed in the core of dying stars and then dispersed into space during supernova explosions. The absence of iron was puzzling. It's also unusual to see any metal sublimating at such a great distance from the Sunday. The massive release of CO2 was likely dragging nickel atoms along with it, but that still didn't explain the lack of iron. Just as with the water vapor, iron eventually made a sudden appearance in the coma. By late September, astronomers began to detect iron for the first time, and the ratio of nickel to iron quickly shifted to a more typical combination. So, while 3I divided by Atlas is gradually becoming more normal, it is doing so in a very peculiar manner. The tail of 3I divided by Atlas has also exhibited some unusual behavior. When we first observed a tail forming back in the summer, it was pointing in the wrong direction towards the Sunday. This is unexpected, as the tail is typically formed by the solar wind pushing material away from the Sunday. This could be related to the early formation of the coma due to the high CO2 concentration. Because the object began sublimating at such a great distance, the solar wind may not have been strong enough to push the cloud of gas and dust away. What we observed was likely an accumulation of this cloud on the warmer, sun-facing side of the object before it encountered a strong enough wind to form a conventional tail. By September 3, I divided by Atlas had developed a short, fan-shaped tail facing away from the sun, which is more typical. The length of a comet's tail varies depending on its composition and distance from the Sunday. For example, comet Hale-Bopp, observed in 1997, had a gigantic tail, but it was also much closer to the sun at about 0.9 AU. Around this time, we had our closest opportunity to observe 3 I divided by Atlas, not from Earth, but from Mars. On October 3rd, the object passed within 0.19 AU of Mars, the closest it will come to any planet in our solar system. Fortunately, we have numerous cameras on and around the red planet. The Perseverance rover captured an image from the Martian surface showing the object as a streak in the night sky. The European Space Agency's ExoMars probe, in orbit around Mars, provided a slightly clearer image, but still not enough to distinguish the bright coma from the object's surface. To get finer detail, we would need a photo from NASA's Mars Reconnaissance Orbiter, which has the most powerful telescope in the Martian system. However, due to a U.S. government shutdown, it is uncertain if this image was taken or when it will be released. For now, we must wait as the sun continues to block our view of 3I divided by Atlas until early December. At that point, we will be able to study the effects of the sun on the object, although our closest view will be from 1.8 AU on December 19th. By then, 3I divided by Atlas will be well on its way out of the solar system. There is one more close encounter to come. On March 16th, 2026, the object will fly within 0.36 AU of Jupiter. While we have fewer cameras around Jupiter, we do have one on the Juno probe, which will have an opportunity to capture one last image of 3I divided by Atlas before it disappears into the interstellar void. At that distance, the object will be cooling down and less active, but its encounter with the sun may have changed it, providing us with a deeper understanding of these interstellar visitors. It's possible that many of its strange characteristics are not from its place of origin, but are an accumulation of peculiarities picked up along its incredible journey. For now, we can only speculate, but more answers and likely more questions are on the horizon.